Assalamu alaikum, students and friends. Today's episode is a follow-up of a previous upload on nuclear radioactivity. This time, focusing on the radioactivity of a beta-minus radioactive emitter. Join me as we describe and analyze this nuclear transformation. So, just hang on, watch and learn. The question is, the sodium isotope undergoes beta-minus decay to magnesium-24, which is a stable isotope with a half-life of 15.0 hours. Initially, a sample of sodium-24 has beta-minus activity of 1.50 microcurie. Question letter A, find the mean lifetime. Question letter B, find the decay constant. Question letter C, find the initial number of sodium nuclei in the sample. And question letter D, find the activity of the sample after 24.0 hours. The nuclear equation involved here is as shown. Sodium isotope with a mass number 24 and atomic number 11 emits a beta minus particle or an electron to become a stable magnesium 24 isotope. Notice that in a beta minus decay such as this, the atomic number of the daughter nucleus is increased by 1, while the mass number is unchanged. The half-life of sodium-24 is also given to be 15.0 hours. Initially, at time equals 0, the sample of sodium-24 has a beta-minus activity A sub naught equal to 1.50 microcurie. And our target variables are, for letter A, the mean lifetime denoted by capital T. The second target variable is the decay constant denoted by lambda. The third target variable is the initial number of sodium-24 nuclei denoted by N naught. And lastly, for letter D, the activity of the sample after a time of 24.0 hours. We first express the half-life, which is in hours, into seconds. Okay, so we just multiply the given half-life 15.0 hours by 3,600 seconds, that's in 1 hour. So we will get the half-life equal to 5.40 times 10 to the 4th power seconds. So for the first target variable, the mean lifetime of sodium-24 is just equal to the half-life divided by the natural log of the number 2, or that is 5.40 raised to the 4th power seconds divided by 0.693. So the mean lifetime, all right, is equal to 7.79 times 10 to the 4th power seconds. The second target variable is the decay constant lambda, which is simply the reciprocal of the mean lifetime. That is 1 over 7.79 times 10 to the 4th power seconds, or lambda is equal to 1.28 times 10 to the negative 5 disintegrations per second. Moving on to the next target variable, the initial number of the sodium-24 nuclei denoted by N0. We need to convert the initial activity A0 of 1.50 microcurie to becquerel. So, we just multiply 1.50 times 10 to the negative 6 curie. Microcurie has been converted to curie. Then multiply that by the conversion factor, which is 3.70 times 10 to the 10th power, all right? That's becquerel per curie, right? And the result, all right, would be A naught is now equal to 5.55 times 10 to the 4th power becquerel. But becquerel, by definition, can also be expressed as decays or disintegrations per second. All right? So, the initial activity A naught, therefore, is equal to 5.55 times 10 to the 4th power decays per second. So we now proceed in computing for N naught, which is just equal to A naught divided by lambda, all right? Or that is 5.55 raised to the 4th power decays per second divided by the value of lambda, which is 1.28 times 10 to the negative 5 per second. So we get, all right, the initial number of the sodium-24 nuclei, N naught, equal to 4.34 times 10 to the 9th power nuclei. Lastly, to find the activity N of the sample after a time of 24.0 hours, we need to first convert 24.0 hours to seconds, which is 8.64 times 10 to the 4th power seconds. And using the formula A for activity equal to A naught, the initial activity, multiplied by the Euler's number raised to the power negative lambda multiplied by the time t. Right? So substituting the given values, we have for A naught 5.55 times 10 to the fourth power decays per second. And then the power for the Euler's number is negative lambda. All right. That is 1.28 times 10 to the negative 5 per second to be multiplied by the given time t in seconds, which is 8.64 times 10 to the fourth power seconds. And simplifying the power of the Euler's number, we get the power of the Euler's number is negative 1.11. And using your scientific calculator, we have the value for the activity capital A equals 1.83 times 10 to the fourth power nuclei per second. Right? Now, when converted back to Curie or microcurie, all right? Because our initial activity A naught is given in terms of microcurie, so our computed value for the activity capital A, 1.83 raised to the fourth power nuclei per second. This nuclei per second is actually equivalent to becquerel. All right? So when you convert this to microcurie, we get the activity capital A equal to 0.495 microcurie in 3 significant figures. So, as expected, the activity, when compared to the inertial activity, all right, is much less. The initial activity A naught is 1.50 microcurie, but the final activity after 24.0 hours, okay, it's now reduced to 0.495 microcurie. So that concludes our tutorial for this topic. Until the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.